An identity is an equation that is always true for any angle. Here in this section we will talk about verifying identities. We want to show that if we have an equation that the left-hand side and the right-hand side are really equal to each other. So we want to prove that. And in order to prove that, we're going to pick one side of the equation to work with. And it doesn't matter if you start with the right-hand side of the equation or the left-hand side of the equation, but we usually start with the side that is more complicated. But it really doesn't matter which side you start with. But what we're going to do is we're going to pick one side and we're going to show that we can use identities and some techniques to change it to look like the other side. So we're trying to show that both sides are equivalent. Now there's no one way to do this. There's several different strategies that we're going to start to use. We can rewrite everything in terms of sine and cosine. That's one strategy. Usually if you do that, things start to cancel out and get simpler to look like the other side. We can use our Pythagorean identities. So if you see a trig function squared and if you see plus or minus 1, usually the Pythagorean identities will be helpful. And we do want to keep in mind that the Pythagorean identities can be rewritten in several different ways. Another strategy that we might use is that if we have one fraction, we can try splitting it into two separate fractions. Or we can try multiplying the numerator and denominator by the conjugate of the denominator. What is conjugate? A conjugate, if you think back to algebra, if I have x minus 1, the conjugate would be the same term in the front and the same term in the back, but the only difference between these two binomials would be the sign in the middle would be opposite. When we multiply conjugates together, the two middle terms will drop out. So if you think back to using that process of FOIL, if I was to multiply these two together, I would get x squared minus 1. So sometimes it's very convenient to take our fractions and multiply by the conjugate of the denominator. And we'll show a couple of examples of that and why it's useful. But that's one of the strategies we want to have at our disposal. If we have two fractions, we would try to give them the same denominator, combine them into one fraction. If we have a complex fraction, we would try to change that to a simple fraction by multiplying by the LCD of all the little fractions. We could also use factoring to help us simplify one side to look like the other. And we use the same techniques that we would use for algebra. And also multiplying, so doing a distribution or going back to that idea of foiling from algebra. Now I want to make a quick little note here. Verifying identities is challenging, takes lots of practice and patience, so they are not easy. And it just takes a lot of practice. You have to not be afraid to get in there, make a few mistakes. If one way doesn't work, then you want to try a different strategy. You can start with the left-hand side and make it look like the right-hand side. Or you can start with the right-hand side and make it look like the left-hand side. There are several different ways that we can verify an identity. So if one way doesn't look like it's getting you anywhere, then we want to try, maybe stop and start over, try a different strategy. The most important thing, I think, is that you do something. Start with something. Start with one of the strategies. Pick a strategy, start with it. Oftentimes, even if you pick a strategy that maybe doesn't work, oftentimes the idea of how you can actually verify the identity will come out of that process. So do something and then go from there. But the worst thing that you can do is sit there and do nothing. So start with one of these strategies and make sure that you're practicing and practicing and practicing to gain confidence and experience with verifying these identities. So we are asked to verify this identity. We're going to start with the side that looks more complicated. So I'm going to choose to start with the left-hand side. And we want to rewrite this so that we achieve the goal of the right-hand side, cosine theta. So the first strategy that we're going to use is we are going to rewrite cotangent and cosecant in terms of sine and cosine. So cotangent would be cosine theta divided by sine theta divided by, and the bottom of the fraction we have cosecant theta. We can use our reciprocal identity to write that as 1 over sine theta. Now we have a complex fraction, but we can simplify this complex fraction by multiplying by the reciprocal of the denominator. So I'm going to take that bottom fraction, I'm going to flip it, and I'm going to multiply it times the top fraction. As soon as we write it that way, we see that sine theta and sine theta would cancel out. So we end up with multiplying across, we get left with ones. Multiplying across, we end up with cosine theta over 1, which of course is the same as cosine theta. And that was our goal. So through a series of identity replacements, changing everything to be in terms of sine and cosine, and simplifying that complex fraction, we show that the left-hand side is actually equivalent to the right-hand side. So we want to verify that cotangent theta plus tangent theta is equivalent to secant theta times cosecant theta. Once again, there are many different ways that we can approach verifying this identity. And you could start with the right-hand side and make it look like the left-hand side, or start with the left-hand side and make it look like the right-hand side. I'm going to start with the left-hand side. And I'm going to choose the right-hand side to be my goal. And in order to start out, I'm going to use our strategy of changing these in terms of sine and cosine. So I'm going to take cotangent theta and write it as cosine theta divided by sine theta. And tangent theta would be sine theta over cosine theta. So there's one of our strategies. The next strategy, one of the other strategies we discussed earlier, was we have two fractions, we want to give them the same denominator, combine them into one fraction. So in order to do that, I would have to multiply the denominators by each other. So I'm going to multiply the right fraction on top and the bottom by sine theta, and the left fraction I'm going to multiply top and the bottom by cosine theta. So now we have that common denominator, that LCD of cosine theta, sine theta. And now that they have the same denominator, I can combine them all into one fraction using that same denominator. So they have a common denominator now. And on top, I'm going to write that as cosine squared theta plus sine squared theta. Now, I see that I have cosine squared and sine squared. When I see a trig function squared, I would suggest that we start to think about a Pythagorean identity. And this is actually directly one of our Pythagorean identities. Cosine squared theta plus sine squared theta, we know that that is equivalent to 1. So we are going to replace cosine squared and sine squared with 1. So there's an equivalent expression that we can use to replace cosine squared, sine squared. We're going to replace that with 1. Remember, the whole idea is to replace it with something that's equivalent within that Pythagorean identity. So now we have 1 divided by cosine theta times sine theta. Keeping our goal in mind, our goal was secant theta, cosecant theta, multiplied together. So let's see if we can get there. Let's rewrite this as 1 over cosine theta times 1 over sine theta. Now you want to be able to convince yourself that if you take that one single fraction and you split it up into these two single fractions multiplied together, that you want to convince yourself that if I do multiply those two fractions together, I do get back the fraction that's above it. So let's verify that. 1 times 1 would be 1. If I multiply across the bottom, I get cosine theta times sine theta. So I can get back to the previous step. Now, why would I want to separate them into two separate fractions? Well, 1 over cosine theta is secant theta, which was my goal, times 1 over sine theta. We can rewrite that as cosecant theta. So we have now verified that the left-hand side can be converted to look like the right-hand side. So these are equivalent expressions, and we have just verified that identity. So we want to verify that sine to the 4th power minus cosine raised to the 4th power is equal to 2 times sine squared theta minus 1. So we want to pick a side to start with. I'm going to start with the left-hand side here, where I have the trig functions raised to the power of 4, and I'm going to choose the right-hand side to be the goal. Now I have sine to the 4th and cosine to the 4th, and on the right-hand side I only have sine raised to the power of 2. So let's start thinking about how I'm going to get rid of these powers of 4. And one way that we can start to break things down to reduce those exponents would be to factor. Sine to the 4th minus cosine to the 4th. If we start thinking back to our algebra days, let's think about x to the 4th minus y to the 4th. If I was going to factor that, that's a difference of squares, and that would factor as conjugates. X squared minus y squared times x squared plus y squared. So these are conjugates. Same binomials, except the only difference would be the sign in the middle would be opposites. So we're going to factor sine to the 4th minus cosine to the 4th in the same way. We're going to factor that as sine squared minus cosine squared times the binomial sine squared plus cosine squared. Now what's really nice about this is that when I look at the right-hand side, sine squared theta plus cosine squared theta, that is one of the Pythagorean identities. And we know that's directly equivalent to 1. So this whole side becomes 1. So now we have sine squared theta minus cosine squared theta times 1. And that just leaves us with sine squared theta minus cosine squared theta. Now we're not quite to our goal yet. Our goal is 2 times sine squared theta minus 1. So our final goal here does no cosine at all. So let's think about how we can get rid of cosine squared. We want to replace that with an equivalent form. So we want to replace cosine squared theta with something that is equivalent to cosine squared theta. Let's go back to this Pythagorean identity. And let's think about what would be equivalent to cosine squared theta within that identity. So we're going to rewrite our Pythagorean identity. Let's subtract sine squared theta from both sides. So that gives cosine squared theta equals, and that's what we want. We want cosine squared theta by itself on one side. We want to know what it's equivalent to. What is an equivalent expression to cosine squared theta? And when we rewrite the identity by subtracting sine squared theta from both sides, we end up with cosine squared theta is equal to 1 minus sine squared theta. So these are equivalent forms. And what that tells us is that when I come back into my verifying my identity, if I bring down my sine squared theta minus, I can actually replace cosine squared theta with the equivalent form 1 minus sine squared theta. So within our Pythagorean identity, we determined these were equivalent. These were equal expressions. So I can come back and replace cosine squared theta with 1 minus sine squared theta. These are equivalent forms. Now I did not replace the negative. The negative was out front of cosine squared theta, and I'm still bringing down the negative. And the negative will be applied to everything that comes with the replacement. So because this negative is out front of these two terms, the negative will have to be distributed back into those two terms. So we're going to bring down the sine squared theta, and now we're going to write it as minus 1, and the negative times the negative would be plus sine squared theta. Now this is convenient because our last step, we see that we have like terms that can be combined. Sine squared theta plus sine squared theta would be 2 sine squared theta. Bring down the minus 1, and now we see that we have achieved our goal. So we want to verify this identity. We have 1 divided by 1 minus sine theta plus another fraction, 1 over 1 plus sine theta. We want to show that the left-hand side is equivalent to the right-hand side, 2 secant squared theta. So we can choose a side to start with. It doesn't matter which side, but I would suggest that we start with the side that looks more complicated. So we're going to start with the left-hand side, and we're going to show that we can achieve the right-hand side. So we have two separate fractions, and one of the strategies that we talked about at the beginning was if I have two separate fractions, give them the same denominator and combine them into one fraction. In order to give these the same denominator, we will have to have an LCD, and we're basically going to end up multiplying the binomials, or those two-term factors, times each other. So we're going to multiply 1 minus sine theta times 1 plus sine theta. And this would be the LCD. So we're going to take the original fractions and we're going to multiply in that missing factor. So we're going to multiply the left fraction by 1 plus sine theta on the top and the bottom. And then the second fraction, we're going to multiply that by 1 minus sine theta on the top and the bottom. Now we're going to FOIL here and here to get our new denominator. So when we FOIL, first times the first, and these are conjugates. And when I multiply conjugates together, the two middle terms are going to end up canceling each other out. So we end up with first times the first, and then last times the last, which would be 1 minus sine squared theta. And on the top of our fractions, when we multiply in those missing factors, we're just multiplying times 1. So here we get 1 plus sine theta times 1, that's just 1 plus sine theta. Plus, the second numerator would be 1 times 1 minus sine theta, which is just 1 minus sine theta. Now, we can combine like terms at the top of this one single fraction. So we see that we get, and let's come down. We see that I get 1 plus 1. Those are common, those are like terms, so I can combine those to get 2. And then sine theta minus sine theta, well, those are going to end up canceling each other out. So I end up with just 2 at the top of my fraction. Now keep in mind that my goal is 2 times secant squared theta. So let's look at the bottom part of this fraction. 1 minus sine squared theta. Let's think about when we see a trig function squared and we see a 1, start thinking about if we can do a Pythagorean identity replacement. So let's take our Pythagorean identity that deals with sine and cosine, And let's see if we can rewrite it with an equivalent replacement for 1 minus sine squared theta. So we want to make 1 minus sine squared theta on one side of our equal sign. Let's see if we can achieve that. Let's do that by subtracting sine squared theta from both sides of this identity. So what we see is that we are able to get cosine squared theta equal to 1 minus sine squared theta. So we were able to rewrite our Pythagorean identity to have that expression 1 minus sine squared theta on one side of the equal sign. And what that means is that it is equivalent to the left-hand side and can be replaced with cosine squared theta. So instead of writing this, we're going to use our Pythagorean identity replacement and write it as cosine squared theta. And of course, this is the same thing as 2 times 1 over cosine squared theta. And let's convince ourselves that if I was to multiply these two separate fractions together, I would get back 2 over cosine squared theta. And now I have 1 over cosine squared theta, which is equivalent to secant squared theta, using that reciprocal identity. And this is my goal. So this was the right-hand side of my identity that I was trying to get to. Here we want to show that these two fractions are equivalent to each other. Now, looking at these two fractions, they both look equally complicated. So in this example, I would say that it would not matter if you started with the left-hand side and got to the right-hand side, or if you started with the right-hand side and showed that you could get to the left-hand side. So for this example, let's go ahead and let's try starting with the right-hand side and showing that we can get to the left-hand side. So let's start here and show that we can achieve the left-hand side as a goal. So let's take 1 plus tangent alpha divided by 1 minus tangent alpha, and let's start to think about what our goal has in it. We're starting with tangent, and our goal has cotangent as the trig function. So let's think about using our reciprocal identity. So let's change this to be 1 plus 1 over cotangent alpha. So tangent alpha is equivalent to 1 over cotangent alpha. And then 1 minus, we'll write tangent alpha on the bottom also as 1 over cotangent alpha. So now we have a complex fraction, and we would like to get rid of the fractions within this larger fraction, and let's multiply by the LCD. So all the little fractions inside this larger fraction all have a common denominator of cotangent alpha. So let's multiply everything on top and the bottom by cotangent alpha. So when we do that, of course we can think about these as cotangent alpha over 1. We get 1 times cotangent alpha, which would be cotangent alpha. And then on the right-hand side, when we simplify this multiplication, the cotangents cancel each other out. So we get plus 1. So here on the left-hand side at the bottom, we have cotangent alpha times 1, which is cotangent alpha. And then on the right-hand side, when we simplify, the cotangents cancel each other out, and we're left with minus 1. And this, of course, was our goal. So very handy to keep in mind what your goal is. We started with tangents, and our answer had cotangents, so thinking about that reciprocal identity is one of the strategies that we can use to verify this identity. To verify this identity, we are going to use one of the strategies that we talked about and outlined on the first page of these notes. We're going to take this fraction right here on the left-hand side. We're going to start with this fraction, and we're going to multiply by the conjugate of the denominator. So we have 1 plus sine theta, and the conjugate to that would be 1 minus sine theta. So I'm going to multiply the top and the bottom by the conjugate of the denominator. Now, why would we want to do that? Well, there's an important reason why, If I multiply across the bottom, of course, we want to FOIL. And when I do that, we get 1 minus sine squared theta. So one of the reasons why we would want to multiply by the conjugate is that if we have just sine theta and we multiply by the conjugate, we get sine squared theta. And when we have a trig function squared, we can start thinking about our Pythagorean identity replacements. So this is an important technique that we can multiply by the conjugate to actually force sine to become sine squared. And then we can use our Pythagorean identity replacements. Now be careful across the top when we FOIL, those are not conjugates, those are exactly the same two terms times itself. So we're going to write that as first times the first, we get 1, outer times the outer, inner times the inner, and then we combine those like terms, we get 1 minus 2 sine theta, and then last times the last, we get positive sine squared theta. So we're using that strategy of multiplying by the conjugate. We FOIL the top and the bottom, and then this is not what we have. And if you think to our goal, secant theta, tangent theta, all of those have cosine theta as a denominator, if I was to think about those as fractions. Well, how can we get there? Well, we notice that on the bottom, now that we multiplied by the conjugate, we have that sine squared theta. What is that equivalent to if I think about my Pythagorean identity? So let's think about our Pythagorean identity here for sine and cosine. 1 minus sine squared theta, let's try to get that on one side of our identity. So let's subtract sine squared theta from both sides. We end up with cosine squared theta is equal to 1 minus sine squared theta. So what we have is that cosine squared theta is exactly equivalent to 1 minus sine squared theta. So instead of writing 1 minus sine squared theta, we're going to write that as its equivalent cosine squared theta. So now we have cosine squared theta as our denominator, and let's now take this one fraction and separate it into 3 separate fractions. So I'm going to write this as cosine squared theta underneath each of the original 3 terms. So 1 over cosine squared theta minus 2 sine theta over cosine squared theta plus sine squared theta over cosine squared theta. So we want to convince ourselves that here they were sharing the same denominator, and if we give them back their own individual denominators, if I were to take these 3 fractions and put them back into one fraction, I would have to have a common denominator. I would keep that common denominator of cosine squared, and I would combine the numerators all on top of that same denominator. So we want to convince ourselves that we can go back to the previous fraction very logically. Alright, so now we have 3 separate fractions, and keep in mind what our goal is right there. We want to get 3 separate terms where one looks like secant squared theta and the middle one is minus 2 secant theta tangent theta plus 2 tangent theta. So I think that we can see that we have the first term already. 1 over cosine theta is secant squared theta. And the last term, it looks like we have that as well. Sine squared theta divided by cosine squared theta is tangent squared theta. Now the middle term is where we might want to kind of think about that a little bit, because we don't have that yet. Let's separate this into 2 separate fractions, multiplied together. So let's think about this as 2 times sine theta, and we're going to separate the bottom as just cosine by itself, so cosine times cosine. So let's convince ourselves that if I multiply these 3 things together, 2 times sine theta over cosine theta times 1 over cosine theta, let's convince ourselves there that we would get back the original middle term. we multiply across the top and across the bottom, we should get back to that fraction. And I believe we do there. Now, what is sine divided by cosine? Well, that would be tangent. So we have secant theta minus 2 times tangent theta times 1 over cosine theta would be secant theta. And we see that we have achieved our goal. Now, you might be thinking, well, the middle term doesn't have the right order. However, the order that we multiply is not significant. So this is actually the same thing as tangent theta times secant theta. So these two things are exactly the same. These two terms, exactly the same. The order in which we multiply is not significant. So this is actually the same thing as our goal. So we have achieved the right-hand side of our identity by multiplying the left-hand side on the top and the bottom by the conjugate of that original denominator. To verify this identity, I suggest that we start with the more complicated looking side, which looks like it would be the left-hand side. So we're going to start here with the left-hand side, and we're going to choose the right-hand side as our goal. So we're going to take these two fractions, and let's think about using our strategy of adding them together by giving them the same denominator. So the LCD of these two fractions would be multiplying those two denominators by each other. So that would be 1 plus cosine x times 1 minus cosine x. So we're going to multiply those denominators times each other. And of course, whatever I do to the bottom of a fraction, I have to do the same thing to the top. So multiplying across the top, I would end up with doing a distribution. So that would be tangent x times 1, tangent x times minus cosine x, so that would be minus tangent x cosine x. All over that common denominator, and let's multiply these together by using FOIL. Those are conjugates, so it's going to end up being first times the first minus last times the last, which would be minus cosine squared x. On top of the second fraction, we're going to also do distribution. So sine x times 1 would be sine x. Sine x times cosine x, that would be plus sine x cosine x. And on the bottom we end up with the same denominator, 1 minus cosine squared x when we FOIL. So now we have a common denominator. Let's keep that same denominator and combine the numerators on top of that same fraction. So we're going to combine all of those terms, we're going to put them all on top of that same fraction. Let's think about doing a Pythagorean replacement for the denominator. We have 1 minus cosine squared x, and to simplify this, let's replace that with its equivalent using that Pythagorean identity. Sine squared x plus cosine squared x is equal to 1. We can rearrange our Pythagorean identity to have 1 minus cosine squared x on one side. So we're going to subtract cosine squared x from both sides. We end up with sine squared x is equal to 1 minus cosine squared x. So instead of writing 1 minus cosine squared x, we're going to do a Pythagorean replacement. So I'm going to rewrite that as sine squared x. Okay. Now we have 4 terms all on top of the same denominator there. And let's start to think about maybe separating this now into separate terms, separate fractions. Let's give each denominator back to its term. So let's write this as tangent x over sine squared x minus tangent x cosine x all over sine squared x plus sine x over sine squared x plus, so each term is going to get back its own denominator, so it doesn't have to share anymore. We're going to separate this into 4 separate fractions, each having their own denominator of sine squared x. Now at this stage we need a lot of things to start to cancel out or to simplify. The first thing that I notice is that I have sine x over sine squared x, so that's going to give us, we're going to cancel here, 1 over sine x. And then the right hand side, the right fraction there, sine x and sine squared x, we have a similar situation. We can go ahead and just cancel those. So we're left with just sine x at the bottom and 1 at the top. Now for the others, they don't have something that will directly immediately cancel out, but we can start to think about changing everything to be in terms of sine and cosine. So these right two fractions, things cancel out pretty obviously, but on the left hand side, these left two fractions rather, things don't immediately seem to cancel out. But let's think about writing tangent in terms of sine and cosine. So that would be sine x over cosine x divided by, and then we have sine squared x on the bottom, minus, and so here we would also have sine x over cosine x times cosine x. So there's the top of the fraction. All of that divided by sine squared x. Now we have complex fractions, but actually this middle fraction, I noticed that cosine x will directly cancel out. As soon as I do that, as soon as I rewrite tangent as sine and cosine, cosines end up canceling each other out on the top of that fraction. So we end up with sine x over sine squared x. And that also can be reduced pretty quickly to be 1 over sine x. So I'm going to go ahead and rewrite everything we have so far that we have simplified. So we have minus sine x, that comes from the middle, 1 over sine x, that's positive, plus cosine x over sine x. So all these are simplified fractions as much as possible. And the last one we need to simplify is this first fraction here. Let's think about this bottom value as a fraction and simplify this complex fraction by flipping and multiplying times the top. When we do that, we see that we have sine squared x at the bottom and sine x at the top, and here we can cancel it as well. So we have 1 and then we have sine x. So when I multiply across the top, we get 1, and then we have sine x times cosine x at the bottom. Now let's go back to see what our goal was. We have now these 4 fractions here that have been simplified as much as possible. Well, let's see what our goal was. Our goal was cotangent x plus secant x times cosecant x. So we definitely have some more simplifying to do to get there. Well, pretty quickly we can tell that minus 1 over sine x plus 1 over sine x, these are exactly the same terms except opposite signs. So these are actually going to just cancel each other out. So we can let those two go. And now we're left with cosine x over sine x, which is cotangent x. So that would be simplified to cotangent x. And then we have 1 over sine x cosine x. And let's separate that into two separate fractions. That would be 1 over sine x times 1 over cosine x. And 1 over sine x, of course, would be equal to cosecant x times 1 over cosine x would be equivalent to secant x. So we have cosecant x, secant x plus cotangent x. And if we look back to our goal, those were the two terms that we had. We had cotangent x, and then we had secant x and cosecant x multiplied together. So if we look back to our goal, we have actually achieved that goal. Remember that the order of the terms is not significant. It doesn't matter the order in which you multiply within the term, and it doesn't matter what the order of the terms is. As long as you have a term that is cosecant x and secant x, and then you have another term that's cotangent x, then we can say that we have achieved our goal. To verify this identity, I am going to start with the left-hand side and show that I can get to my goal of the right-hand side. And one of the reasons why I'm going to choose to do that is because we have basically a Pythagorean identity right there. 1 minus cosine squared. We know that sine squared alpha plus cosine squared alpha is equal to 1. And I want to replace 1 minus cosine squared alpha with sine squared alpha. So I'm going to use my Pythagorean identity to show the equivalency. So I'm going to subtract cosine squared alpha from both sides. And we end up with sine squared alpha is equal to 1 minus cosine squared alpha. So I'm going to replace 1 minus cosine squared alpha with sine squared alpha. I notice that my goal is written only in terms of sine. There are no cosines. So I'm going to replace cosine squared alpha with its equivalent also within the Pythagorean identity. And you want to be careful about something. When we look at the Pythagorean identity, the original identity, there's no way that I can get a positive 1 and a positive cosine squared alpha on the same side. Either I'm going to subtract cosine alpha from both sides, then I end up with a negative cosine alpha, or I would end up subtracting 1 from both sides. However I manipulate that Pythagorean identity, there's no way that I'm going to be able to get on one side of our equal sign the whole entire expression 1 plus cosine squared alpha. So I'm not going to try to replace the entire expression. So I'm going to keep the 1. So when I rewrite this, we're going to keep sine squared alpha, and I'm going to keep the 1 plus. And I want to just replace the cosine squared alpha with its equivalent. So I'm going to take the original identity and I'm going to rewrite it in terms of cosine. So I'm going to say, let's get this by itself. So that's cosine squared alpha. Subtract sine squared from both sides. We end up with 1 minus sine squared alpha. So I'm going to replace cosine squared alpha with its equivalent in terms of sine, 1 minus sine squared alpha. Now I'm going to simplify within the parentheses. That's 1 plus 1, which is 2, and then minus sine squared alpha. Now if I look at my goal, I see that I'm really, really close, but in order to get there, I'd have to distribute the sine squared alpha. So I get 2 times sine squared alpha minus, and then sine squared times another sine squared would be sine to the 4th. So I get my sine raised to the 4th power of alpha. And that is my goal.